Good afternoon, everybody. Today we're going to do a calculus problem. It's going to involve the disk/washer method, more accurately the disk method, since we don't have a hole in the middle. You could think of a disk as a washer with no hole in the middle, informally. We are going to find the volume of the solid generated by revolving the shaded region about the x-axis. And well, what is a shaded region? The shaded region is the region here bounded by the y-axis, x equals pi quarter, which is here, and the graph y equals secant x, which is here. And let me zoom. This is awful blurry. Let me maybe zoom out a little or zoom in. Well, okay, y equals 6 secant x. I'll put this on the board where we can see it better. So x equals 0, aka the y-axis, x equals pi quarter, y equals sec theta. And instead of x, I'm going to use theta. So humor me there. Okay, so here is, my drawings are not as good as their drawings, but we can at least see it better. So there's the y-axis. Here's the theta axis. Our bounds from theta equals 0 to theta equals pi quarters. Okay, and notice I've drawn a very thin black rectangle here. I've imposed that inside our graph. Really, I've not imposed it. It's already part of the graph anyway. I'll explain why I drew this important rectangle here in a moment. Now, never minding the rectangle just for right now, if I revolve this region, this striped region about the theta axis, catch myself there, the theta axis, I get this blowhorn looking object right here. My drawing is not perfect. I tried my best. Now, in the process of revolving this region about the theta axis, this black rectangle, infinitesimally thin, very, very, very thin, is also going to get revolved. And when it gets revolved, it's going to create a disk in the YZ plane that's whose thickness is along the x-axis, or parallel to the x-axis, but the thickness is extremely thin. D theta is the thickness, the very small thickness. So, and this drawing is relatively bad, but here's a disk. It's a very, very thin disk. It goes along the YZ. Follow my finger. Well, I can't keep it into the camera. It's a YZ disk, but whose width is along the x-axis, but is very, very thin. And I tried in vain to draw that here, or I didn't draw it too well. It gets the job done, but it's not great. Now, for this very, very thin disk, if I choose any face of the disk, the area of that cross-sectional face is going to be pi r squared. That's just it's a circle. The face is a circle. So a sub theta is going to be pi r squared. But r, we're not really going to use r. We're going to use 6 sec theta, because that's what the radius is, this little radius chord right here. It's 6 secant theta, and that follows from the fact that the rectangle had a y height along y of 6 sec theta when we revolved it around. We create a diameter of 12 sec theta and a radius of 6 sec theta. Okay, and we do pi times the square of 6 sec theta to get the area of just a circular cross-sectional of the disk, which is very thin. Now, when we square 6 sec theta, we get 36 sec squared theta, and there's the pi that just tags along. Okay, and now if we multiply the facial cross-sectional area by the very small thickness d theta, we get the infinitesimal volume of the infinitesimal disk. So dV is the infinitesimal volume of the infinitesimal disk. I can't really say washer because there's not a hole in the middle, even though it is related to the washer. So dV is that, and naturally every fiber in our being wants to put integrals on right here with the dV, and an integral right here with the 36, and that's pretty much what we do, sort of, kinda. It amounts to the same thing. What we're going to do is add infinitely many of these infinitesimally thin disks, and that will give us the true volume of this blowhorn looking object. Now, really, when I say that we're adding infinitely many, infinitely thin things, that's a little bit informal. But for the purposes of what we're doing here, that's okay. Analysis would give you a more precise language. But we're, in formal terms, we're adding infinitely many, infinitesimally thin disks that are in the YZ plane and whose small thicknesses d theta lie along the theta axis. A minute ago I said the x-axis, I meant the theta axis. Pardon me there. I can't catch myself when it comes to x and theta. I need to use theta. Okay. Now, so let's just do the problem. Now, I'm just going to, so the volume, it's the area. We integrate the facial area of all the infinitesimally thin disks. So we integrate all these infinitesimal volumes. A theta d theta is an infinitesimal volume, and we integrate over these infinitesimal volumes from A to B. There are boundaries. There are theta boundaries. Let me point out that in the disk and washer method, we're not doing shell yet. So no shells yet. In the disk and washer method, we are integrating about the axis that we revolve around. I don't want to say the word rotate, I want to say revolve. If I did say rotate earlier, scratch that, we're revolving. So the volume is the A to B integral A theta d theta. We're revolving. So that's the 0 to pi over 4 integral of pi, quote unquote, r squared, 6c. This is the same thing that we're doing before, except we're putting the integral there. We're just sticking this integral in, and we're integrating over these pi r squared d thetas, these infinitely small, quote unquote, volumes, infinitesimal volumes. Pi r squared h, which is the volume. By the way, the volume of a disk is pi r squared h. This is the pi, this is the r squared, this is the very small h. The h is the thickness. And so that's going to be, now we just, we square 6 sec theta, that's 36 sec squared theta times pi, integrating from 0 to pi quarter. We can yank the 36 out, it's just a constant. Wait, I need to be over here. We yank the 36 out, it's a constant, 36 pi, 0 to pi quarter integral, 6 sec squared theta d theta. Just sec squared theta d theta, just the secant squared. The 36s are being yanked out. Now we know what the integral of secant squared is. It's the tan of theta, the antiderivative of the sec squared, along our lower and upper bound. So there's that. And so we got 36 pi times the tan of the upper bound minus the tan of the lower bound inside parentheses or brackets. Now the tan of pi quarter from trig is 1. The tan of 0 is 0 itself. So that just amounts to 36 pi. And that is our final volume. That's it. 36 pi is the volume of this blowhorn 3D object that I've tried to draw in 3D here. I hope this helps. This is called disk method integration, finding the volume by using the disk method. Here later on I'll do some volumes over its first cousin, the washer method, which is very closely related. But this is just the disk method for now. Again, what I did was what it amounted to. I stuck an integral here with the dv and an integral with the 36. Integral means informally that you're adding infinitely many, infinitesimally small things. That's a little informal, but for our purposes, cheers. That's good enough. We're adding the volumes of infinitely many, infinitesimal disks to get the volume of the blowhorn. Thank you guys, and I'll try to do more videos shortly. And again, one last thing, with disk and washer we integrate about the axis that we revolve around. And if I said rotate earlier, scratch that, I meant revolve. We integrate about the axis that we revolve around. And I hope this helps. And thank you.